Welcome to Brain Vision.
So here we have heat flowing out of the water and into the ice. The net heat flow for the entire system is 0. The ice warms to 0 degrees Celsius, melts, and then the water from the melted ice warms from 0 degrees Celsius to the final temperature. First, we'll calculate Q for each component of the system, and we'll neglect the mass of the beaker. So we'll use the equation Q is equal to mc delta T, firstly for the water. So for our 0.25 kg of water, and this water cools from 75 degrees Celsius to 30 degrees Celsius. This water does not change phase. So QW, Q water, is equal to mc delta T, where m is the mass of the water, C is the specific heat capacity, and delta T is the change in temperature. So we have 0.25 kgs of water times its specific heat capacity, 4190 joules per kg Kelvin, multiplied by a change in temperature of 30 degrees Celsius minus its initial temperature of 75 degrees Celsius. Hence we get the heat lost by the water, since the water is now being cooled, is 4.714 times 10 to the 4 joules. The negative sign implies the heat flows out of the water and into the ice. Next, we'll calculate the heat gained by the ice as it warms to 0 degrees Celsius, melts, and then the water from the melted ice warms to 30 degrees Celsius. So here we have a slightly different equation. The heat gained by the ice, Q, is equal to the mass of ice, we'll call it M, this is unknown, times the specific heat capacity of the ice, times delta T, plus the mass of ice, M, times the latent heat of fusion in turning the ice into water, so we're going from a solid to a liquid phase, plus this mass of ice which now turns to water times the heat capacity of water, Cw, times the change in temperature to get to the final temperature of 30 degrees Celsius. So putting all this together, we get that this is M, which is the unknown mass of ice, into the specific heat capacity for ice is 2100 joules per kg Kelvin, times delta T, which is 0 minus 20 degrees Celsius, which is 20 Celsius degrees, plus the latent heat of fusion going from ice to water is 334 times 10 to the 3 joules per kg, plus the specific heat of water, which is Cw, which is 4190 joules per kg Kelvin, multiplied by a temperature change of 30 degrees Celsius minus 0 degrees Celsius. So the water that has been melted goes from 0 degrees Celsius to 30 degrees Celsius. So that's the temperature change of 30 Celsius degrees. And doing this calculation with our one unknown, we get the heat gained by the ice in terms of its mass is 5.017 5.017 times 10 to the 5 joules per kg multiplied by its mass m. So now we have the heat gained by the ice and the heat lost by the water that was initially in the system. So what we do know is that Q for the system is equal to 0. The energy is conserved. So this implies that the heat for the water, the heat lost by the water and the heat gained by the ice must equal to 0. And so if we put our values in here, we get QW, which is minus 4.714 times 10 to the 4 joules, plus the answer for the energy gained by the ice, which we calculated to be 5.017 times 10 to the 5 joules per kg times mass m is equal to 0. And hence we have an equation with one unknown, which is the mass we wish to solve for. And therefore, the mass of ice that needs to be added to the system in order to achieve everything explained above is 0.094 kgs. So since the final temperature is 30 degrees Celsius, we know that all the ice melts and the final system is all liquid water. The mass of ice added is much less than the mass of the 75 degrees Celsius water, and hence the ice requires a large heat input for the phase change.